Okay, so we're going to do our entry task today for Monday or Tuesday's class on December 7th or 8th, depending on which period you have. I set it up in my notebook, and if you haven't been using your notebook, try to remember to use that as much as you can. Keeping the information in one spot is important. I'm only on page 12 because Mr. Peterson was teaching for so long that I didn't use my notebook very much. So whatever page you're on, make sure you add that into your notebook. So the first one, what is the mass of a rock accelerating at 2 meters per second squared that was thrown with a force of 7 newtons? So I'm going to do what I would do before is circle what I need. What is the mass? So I'm looking for mass. And I'm going to underline everything that I'm given. It's accelerating at 2 meters per second squared, and it's thrown with a force of 7 newtons. So this is a situation where I'm looking for mass. I'm given an acceleration and a force. We know that we have the standard equation, force equals mass times acceleration. If you can't remember how to rearrange an equation using algebra, you can use the circle. If we're looking for mass, we cover up m, and then we're left with F over top of A, so force divided by acceleration. So our equation we'll use for mass is force divided by acceleration. So we need all three of these variables, mass, force, and acceleration, or FMA. We need all of them. So what is given to us and what we're looking for is what we'll fill out here in the variables. So force is given to us at 7 newtons. Mass is what we're looking for, so that's going to be x kilograms. Acceleration is given to us at 2 meters per second squared. And now we're going to take these variables and we're going to plug them into these variables over here in the order of the equation. So m is x kilograms equals, force is on top, so 7 newtons, dividing that by our acceleration on the bottom, 2 meters per second squared. And now we just divide. What's nice about this is this was a simple problem. You could probably do it in your head. 7 divided by 2 we know is 3.5. And we know we need kilograms because that's the unit for mass. Well, let's talk about how we get kilograms. Remember what a newton is. A newton is a kilograms meters per second squared, because to get to a newton, you have to multiply a mass by an acceleration. So when we break it down, that helps us understand how do we get to kilograms in the end. So we just cancel what's on top and bottom that's the same. We have a meters per second squared on the top. We have a meters per second squared on the bottom. That leaves us with kilograms. That happens to be exactly what we need. And we get 3.5 kilograms as our mass. So that one should be pretty easy. Remember, if we're solving for acceleration, we'd cover up the A and get force divided by mass. If we're solving for force, we'd cover up the F and get mass times acceleration. Okay. If a crane is pulling up a 1,750 kilogram car, that's a mass. What is the upward force? So I'm going to circle that whole thing. It will need to use to hold the car above the ground in equilibrium. So this is one of those questions where we have this vocab word here. I'm going to put a box around equilibrium. You've got to know what they're asking for. Equilibrium, if we remember from the notes, equal kind of gives us this hint. When we're talking about equilibrium in forces, we want to know, are the forces needing to be balanced or unbalanced when you're talking about equilibrium? And if you think about the word equal, that means that the forces need to be balanced. And remember, there's two things that could be happening when the forces are balanced. An object can be still, meaning holding still and not moving, or an object can be moving at a constant velocity. If it's moving at a constant velocity, its forces are still going to be balanced, which would give us a net force of 0. If our object is holding still, our forces will also be balanced at a net force of 0. So equilibrium means balanced forces. So I'm going to draw this one out just for the sake of knowing kind of what is it that I'm looking for. So if I have this crane, you guys, I'm terrible at drawing, so just note that. Here's my crane, and it's going to have this cable somehow holding up this car. Here comes my awesome car drawing. It's going to be kind of like a round car. There we go. There's my car. So I'm only given one number, but in order to have the forces balanced, I have to have equal upward and downward forces and side to side, but it's not moving right now. The crane is just holding it. We want it to be still, not moving forward or backwards or up or down. It's just an equilibrium hanging from this crane here. So that means the upward and downward force need to be equal. Well, I'm only given mass. So mass is one of the things that I know I have at 1,750 kilograms. That's the mass of the car. Well, we also know that mass is really important to find force, but it's also important to find our weight. And remember, what is weight? Because weight is technically a force. Oops, sorry, did that backwards. So force weight is equal to what we call our weight here in physics, the problems we're doing. And remember, weight equals mass times gravity. Because it is a force, we have a mass, and we know that gravity is an acceleration. If we multiply a mass times an acceleration, we have a force. In this case, since it's pulling downward, we're using gravity as our acceleration. So you do have to know Earth's gravity in order to solve this. And we've talked about it many times at 9.8 meters per second squared. Now, some of you might wonder, well, should I put this as a negative number because it's gravity and it's pulling downward? If we were to draw it on a force diagram, yes, it would go downward because it would be kind of pulling downward in the negative direction while something would be pulling upward in the positive direction. But whenever we do gravity in an equation for something like weight, or we'll use it for potential energy later, you do not use gravity as a negative number. You can't have a negative force weight. Just doesn't happen. So if you stand on something and it pulls you down towards the planet or the moon or whatever you're standing on, or if you get on a scale, it pulls you downward, that's gravity pulling you down, but you can't have a negative weight. So you have to know that when we're solving, we're using a positive number. But if we draw it on a force diagram, we can know that it's pulling downward and it would balance out as a negative number. Okay, so now that we know that we need the force weight pulling downward of the car, if we can get the weight of the car, we can safely say that, oh, well, we'll have to balance that out with the upward force of the crane pulling upward. So we have our two variables of mass and gravity, and that's going to give us our weight in newtons, because remember, it is a force. So I'm going to use this equation, weight equals mass times gravity. X newtons is my weight. I need the mass of 1,750 kilograms. And I'm going to multiply that by 9.8 meters per second squared. And that is going to give me the downward weight or downward force the car is pulling on the crane. So how I would do that in my calculator is I would just do 1,750 and I'm going to multiply that by 9.8 and it gives me 17,150. And remember, a kilograms meters per second squared is a newton. So that's telling me that downward force or weight is 17,150 newtons. Now, if I'm drawing this on a force diagram, I technically could put a negative there to remember it's pulling downward. Now, if I'm answering it in a weight question, you never make the weight negative. Weight is never negative. But if I put it on a force diagram as a downward gravity force, then I'm going to add that negative. Now, to balance that and make it equal, in equilibrium, so it's not moving, we would have to have an equal upward force, which would be of a positive 17,150 newtons. These now, if I add them together, are going to give me a net force of 0. Net force of 0 means that I have balanced forces and the car won't be moving. So the key was, note that I asked for the upward force. Some kids in my last period said, well, if it was balanced, the net force is 0. Correct, but I didn't ask for the net force. I asked what the force, the upward force would be needed to balance it and keep it in equilibrium. So that's the key there, reading what I'm asking for. Okay, so upward force of 17,150 newtons. Now the last one is going to be asking a net force. So now we are looking for net force. What is the net force on a crash test car that was hit from behind? This is important, with 216 newtons of force, and from the side with 462 newtons of force. So again, draw it out so you can kind of get the idea of what you're looking at. Okay, so I got my car. So good at cars. So my car now is being hit in two directions. Once from behind, and it's a crash test car, so they're really banging it up to try to see what happens. So 216 newtons of force came from behind, while 462 newtons of force came from the side. So now we have forces coming at a right angle. Now, if you remember, when we're looking for net force at a right angle, we have to use the Pythagorean theorem, which is a squared plus b squared equals c squared. So we note that this 462 newtons is a bigger force than the force from behind. So we probably will end up having our force go off in a direction diagonally, but more pushed diagonally this direction because this is a larger force. So thinking about that, of which force it will be applied to it in a diagonal direction. So it doesn't really matter which one of these are A or B, but remember, the Pythagorean theorem tells us that, let's say this is A and this is B, this is going to be C, the hypotenuse of the triangle. That's what we're trying to find there. Okay, so A squared is going to be 216 newtons. And I'm going to put parentheses around it and put the squared on the outside. That reminds me to square everything inside, including the newtons. I'm going to add that to B squared, which is 462 newtons, parentheses squared, still equals C squared. Now, I know when Mr. Peterson did it, or you've maybe seen it before, you can get rid of the squared ahead of time on the C by square rooting the whole equation and then entering everything in. I just like to bring it down all the way to the end and then square root it. So either way works. If you prefer the other way, you could do that as well. So now I'm going to square these. So you can do it two ways. You can use your calculator with the squared button if you have one, or you can multiply that number by itself. So I'm going to start with that method. 216 times 216 equals 46,656. And notice I'm also going to square my newtons. Newtons squared. Because later I'm going to get rid of that squared by square rooting everything. So keeping it there is important for the problem. Now I'm also going to show you the other method. If you have like a phone that you can turn sideways or you have a squared button, 462, instead of multiplying it by itself, I'm actually going to hit the squared button, which is the X2 button, and I'm going to get 213,444. And that's also Newton squared equals C squared. So notice I'm still bringing down my C squared. So now I have to add these together. I have like terms. I have a Newton squared and a Newton squared. So I have 213,444 plus 46,656. Oops, my phone turned upside down. 46,656 equals 260,100. I'm adding like terms, so it's still Newton squared equals C squared. So we all know that I don't want the squareds there. We got to get rid of the squareds. So we've got to get rid of this Newton squared, and we got to get rid of this C squared. So we're going to do the opposite, which is square root. And if you have a square root button, I know on my phone, it's this button right here that says a square root around an X with a little 2 on the inside. I'm going to hit that. It's going to give me 510. And since I square rooted the newtons as well, just newtons by itself equals C, because I got rid of the squared there. So that's telling us that, and we could draw out all those triangles. Remember how Mr. Peterson talked about the different triangles if you'd like the trig. But we're going to be kind of going in the direction of a diagonal way from this. So we're not going to be perfectly diagonal, probably not even that much. More like this. Okay. And you're being hit from the side, hit from the front. You're going to kind of move off to the diagonal since this was the stronger of the two. Okay. So that is 510 newtons of force. Oops, and I forgot to go ahead and do that right there. All right, that is the entry task.